Welcome. This video is going to continue the discussion of section 5.2. We're going to be talking about geometric series in this video. And the first thing is, you may or may not remember, back when we were doing improper integrals, we explored this particular improper integral, and we talked about being convergent for some values of p and not for other values. Well, that's going to kind of lead to one series that we're going to look at called the p series. We'll take a look at that in future sections and use it quite extensively. But another series that we're going to look at is what's called the geometric series. And the way we get the geometric series is that each term is obtained by multiplying by a common ratio r. And what we do is we take that r times the previous term. So this is an important note. Because we get each term by multiplying the previous term by r, that can help us actually know how to find r. We can find r by using division, right? We can find r by dividing any term by the term before it. So definition, we have the box here, has the form of a geometric series. And this series converges or diverges depending on the value of r, depending on that common ratio. So if it turns out if the absolute value of r is less than 1, the series converges. If the absolute value of r is greater than or equal to 1, it diverges. And if it does converge, we actually have a formula for what that series adds up to. It's the sum of that geometric series is equal to the first term a over 1 minus r, the common ratio. So this first term, a, is going to denote the first term. How do we know that? Well, it says right here, right? It lists out the terms of this series, and it lists the first term as a. That's what you get when n equals 1. You basically, when n equals 1 on this formula, this becomes a. So that's the first term. Again, r is the common ratio. And let's take a look at some examples. So example 2 says determine whether the geometric series converges or diverges. If it is convergent, find its sum. Right. Well, how do we know if a series is convergent? How do we know if a geometric series is convergent or divergent? Well, again, going back to our definition here, it only converges if the absolute value of r is less than 1. If it's greater than 1, it diverges. So we need to know what r is. Well, r is really easy to tell in a geometric series because it's the value here. R is the value that we're raising our power to. So in this case, we have 0.1 raised to the nth power. That means r is equal to 0.1, and that is less than 1, right? If we're comparing to 1, that is less than 1, which means the series converges. So that means it converges. We also need to find the first term, and you need to be careful here because you need to note where this series starts. It starts with n equals 0. So our first term is going to be 0.9 times 0.1 raised to the 0 power. Of course, anything raised to the 0 power is 1, so our first term is 0.9. And so it converges. Our first term is 0.9. That means our sum, remember our sum is right here. It's a over 1 minus r. So it's a, this is a over 1 minus r, which in this case is 0.9 over 1 minus 0.1, which is 0.9 over 0.9, which is 1. So the series converges, and it adds up to 1. All right, let's take a look at the next one. Now, it was easy to tell what r was in the last one because the 0.1 was raised to the nth power. It doesn't specifically tell us here. It just tells us that this is a geometric series, and it tells us the first 4 terms. So again, you get from one term to the next by multiplying by r. So if we divide, we can figure out r. So we can take 4/9 divided by its preceding term, divided by 2/3. Of course, this is the same as 4/9 times 3 over 2. And we can simplify there. So this simplifies to what? That simplifies to 2/3. And that should make sense. If you take 4/9, for example, times 2/3, you get 8 over 27. And if you take that times 2/3, you get 16 over 81. So r is 2/3. Again, that's less than 1. Can we say, therefore, the series converges or diverges? The series converges. And the first term, we know a is equal to 2/3. We can see that right here. There's the first term. So we know that this infinite sum is equal to the first term, 2/3, over 1 minus r, which is 2/3. So this is 2/3 over 1 minus 2/3 is 1/3. That means that this adds up to 2. So the sum of that geometric series is 2. We have another one that's the same. I'm going to go ahead and let you figure out this one on your own. So go ahead and pause the video, and then we'll talk about the solution. Okay, so we start by finding r. We just divide 2 consecutive terms. So -1/2 divided by its previous term is -1/2, which means the absolute value of r is equal to 1/2, which is less than 1. So again, it converges. We also know the first term is 1. So when you plug those into our formula for the sum, we end up with 2/3. So hopefully that makes sense. We also have here in Theorem 5.7 some properties of series. Most notably, you can see that if you have a series, if you have 2 separate series, A sub n and B sub n, and they're both convergent series, then we can separate those into a sum of 2 series, right? So if we have something like this, we can rewrite it like this. And the same goes with subtraction. We can also pull a constant inside the series out in front. So we can use both of those. So say we have this series in example 3. Right off the bat, it kind of looks geometric, but it's not really geometric, not looking at it. It's actually a difference of 2 geometric series, but we need to kind of do some manipulation to see that. So rewriting this, we have 3 to the k plus 1 minus 2 to the k over 5 to the k. And we know we can split this fraction. So we can split this as the sum k equals 1 to infinity of 3 to the k plus 1 over 5 to the k, and minus the sum of 2 to the k over 5 to the k. And let's do some algebra work on the side here. So using some rules for exponents on the side, we know that if we have 3 to the k plus 1, we can use the product rule, and we can say that that's 3 to the k times 3 to the 1, which is just 3. So we can say this is 3 times 3 to the k. Well, that's helpful because these powers in the numerator and denominator are different in this first sum, or the first geometric series. The second one, notice they're the same power, so we could rewrite this second one as 2/5 to the k, which is definitely a convergent geometric series, right? Because r is 2/5, so 2/5 is going to be less than 1. This one, though, it's not the same power, but if we rewrite 3 to the k plus 1 as 3 times 3 to the k, we have the sum of 3 times. We can pull that 3 out front, and then we have 3 to the k over 5 to the k, which, just like the last one, we can rewrite that as 3/5 to the k. So we have 3/5 to the k power, which is, again, a geometric series that converges. So let's make a little note of that. This is absolute value of r is 3/5, which is less than 1, so it converges. And same thing here. Absolute value of r is equal to 2/5, which is also less than 1, so it converges. For this first one, if we take, I didn't write it, but this is k equals 1 to infinity, right? So when k equals 1, the first term is 3/5. So we have a equals 3/5, and likewise, the first term of the second geometric series is 2/5. So they both converge, which means we can use that sum formula on both of these. So this series is equal to 3 times what this convergent geometric series adds up to. It adds up to, remember, a convergent geometric series, a times r to the n minus 1 is equal to a over 1 minus r. So a in this case is 3/5 over 1 minus 3/5. Then we have minus, and then we have the sum of the second one. This is going to be 2/5 over 1 minus 2/5. And we can do some algebra here. This is 3 times 3/5 over 2/5 minus 2/5 over 3/5. This is equal to 3 times 3/2 minus 2/3. And if you do the math on that, that comes out to 23 over 6. So it turns out that that series does converge, and it converges to 23 over 6. And in other words, if you add up all the terms in that sequence, they add up to 23 over 6. There's one more example here in this section, this example 4, which takes a look at the harmonic series, and it basically just makes the statement that the harmonic series, and this is one you're going to want to remember, it always has the form 1 over n, that one always diverges, which is kind of a little bit not intuitive, because those terms in the sequence are getting smaller and smaller, right? So the sum looks like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. So each time you're adding a smaller and smaller number, but it's not adding a smaller number fast enough to make this series converge. And so this one actually diverges. And again, this is an important series. You're going to want to remember that fact. And that's going to do it for this section. That's the end of section 2.1. I'll see you in the next section. Thank you.